Hey everybody. I mentioned in class today being Thursday, that I would make a quick video about just the Newton's law of cooling. So this is kind of a standalone lesson, um, especially if you're having trouble with those questions in the homework. My hand looks weird. Um, but this isn't a huge deal. It's not like you should really sweat it too much, but I think there are interesting problems here. I feel like these real world application type of problems, even though they're a little bit goofy, might be a little bit useful for some of you to look at, especially as we move into the next topic. So check it out. All right, so Newton's law of cooling, we've mentioned already, so I won't spend too much time with the derivation. On Thursday, we used the differential equation. Rate of change of temperature is proportional to the difference in temperature between the object and the surroundings. Separation of variables, we brought all of the uppercase T, the temperature, to the left side, lowercase t's to the right side. K could have gone anywhere, but I chose to bring it to the right side. Integrate both sides, and then do some algebra to solve. So you can check out the video from Thursday's lesson if you want to see that in more detail. Basically, we come up with this solution to the differential equation. The temperature as a function of time is some constant times e to some other constant times the time plus the temperature of the surroundings. So the first situation I want to take a look at is if we have a pizza removed from a 425-degree oven set in a room to cool that is 72 degrees. After 10 minutes, the temperature of the pizza is 350 degrees. I would like to know eventually how hot is the pizza after another 10 minutes and when will the temperature be 100 degrees. Now those two questions are both going to be very easy once we have an equation. Right now, my general equation looks like this. If I knew the values of A, K, and T sub S, it's easy. What's the temperature after 10 minutes? Plug in 10. What's the temperature, or when will the temperature be 100 degrees? Set it equal to 100 and solve. The problem is coming up with these constants. Whoops. It's going to be a little bit more difficult. Not bad. Actually, honestly, we're done with the calculus. The rest of this is going to be a bunch of algebra. Starting with the value of the temperature of the surroundings, we're given that in the statement of the problem. We're given that that is 72 degrees. So we can plug that in. As for the rest of it, I'm going to say that the temperature at time equals 0 is 425. So if I plug 0 in here, we end up with 425 equals A times e to the 0, which is just 1, plus 72. So that actually goes pretty quick once you plug that in. I'm going to skip a lot of the algebra so this video doesn't end up being too long. But when you do that, you should solve it, and you'll get A equals 353. And again, that comes from a relatively simple equation that is basically 425 equals A times 1 plus 72. So this just comes from 425 minus 72. And then once I have that, I've got those two constants. And so if I use the other condition that we're given, that T of 10 is 350, that means that when the temperature is 350, 10 minutes have gone by. I know my constant A, e to the k we don't know yet. I'm plugging 10 into this equation. So 10 times k, whatever that is, plus the temperature of my surroundings is 72 degrees. And so the only thing we don't know here is k. I'm going to go more into detail a little bit later with how this goes, but this is just algebra. Subtract 72, then divide by 353, and then undo the exponent with the natural log, then divide by 10. Ultimately, when you get done with this one, you should have k approximately equal to negative 0. Let me see where I wrote this. Negative 0.02388 approximately. So at this point, we have our equation, and I can go back and I should be able to solve these fairly easily. And maybe I'll type this, it'll go a little bit faster. The temperature as a function of time, as I have found, is 353 e raised to the power of negative 0.02388 t plus 72. By the way, if I graph this equation on Desmos, we can see that this actually looks exactly like what we think it should look like. Initial temperature, the temperature at time equals 0, is 425. Perfect. It's cooling down fast at first. And as it gets cooler, as it approaches room temperature, which, by the way, let's just graph that. No, it doesn't like uppercase T. I guess I'll have to trick Desmos and just call that Y. So there is our room temperature, and we see that our graph, our temperature function, approaches that and then just hugs that for the rest of the graph. So it decreases fast, slows down, approaches that value, which is consistent with what it should be doing. And then maybe before I move away from this, I could find when this is equal to, no, I can find what is the temperature after 10 minutes. So I can just find at time equals 10, we got a temperature of 350. Whoops, we already knew that. After 10 minutes, and then I ask, what is the temperature after another 10 minutes? So we'll go to time equals 20, and I get 290.93, so about 291 degrees, which, by the way, we could just plug into this function. No big deal there. And then my next question, I believe I'm asking, when is the temperature equal to 100? This one's a little bit less easy because it's not lining up perfectly on a nice number. It looks like it's around 106.3 minutes, so about an hour and 40 minutes after we pull it out of the oven. When I solved this using algebra, I got 106.104 minutes, and so we're just a little tiny bit off. And so again, first question we can answer by plugging in time equals 10. I got, what was that? 290.9. Oh, take that back. I made the same mistake I just made on Desmos. At time equals 10, the temperature is going to be 350. At time equals 20, so 10 minutes later, after another 10 minutes, the temperature would be 290. I'll go with 290.9 degrees, roughly. And then when will the temperature be 100? I'll set my equation equal to 100. So 100 equals 353 e to the negative 0.02388 t plus 72. And then you guys are algebra experts at this point. Subtract 72 from both sides, divide both sides by 353, natural log to undo the natural exponential, and then finally divide by negative 0.0238. You should come up with about 106.1 minutes later. So that's the idea on that one. The second part of my question looks like this. After a few pieces have been consumed, the lonely pizza eater decides he wants to put it in the refrigerator. And so we're looking at the pizza is down to 100 degrees. So we're assuming that the pizza is at 100 degrees from the previous situation. I'm going to place it into the 40-degree refrigerator. So maybe I'm going to give you a second just to process what you're reading. So at this point, our temperature of the surroundings are now 40 degrees, but everything else is staying the same. Those other two constants, the K value, that was just the temperature that pizza warms or cools down at, and that A, well, I guess we'll have to do a little bit of work to find that A. Most of the equation stays the same. My temperature of the surroundings, I just switched to 40 to account for the new temperature of the surroundings in the refrigerator. This constant is the constant for that pizza. Then this constant We'll just have to find what that is using our new initial condition. I'll say that at time equals, actually, I think I'm going to cheat ahead. I think I've got this on the next slide. Time equals 0, our pizza is at 100 degrees. So that'll let us easily solve if 100 equals a times e to the 0, which is 1, plus 40. That tells us that our value for a is 60. 100 equals what plus 40? And so I plug that in for a. I've already got my t sub s, and now I've got my equation. So how long is it going to take before it's cooled to 60? I set it equal to 60, and then do the same algebra that we've been doing. Subtract 40, divide by 60, natural log, divide by negative 0.02388. When I did this, I got that it's going to take the pizza about 46 minutes. It was 45.996 minutes. So I'll say that, I'll just switch this to approximately. We'll say that it's roughly 46 minutes. And then one final situation for us to look at, one final Newton's law of cooling situation. I'm going to take a can of Tab, the refreshing and robust flavor of Tab, out of the refrigerator so I can quench my thirst without consuming too many calories. If the delicious and robust beverage has a temperature of 45 degrees after a half an hour, how long is it going to take before it's at a virtually undrinkable 60? So now my initial temperature is 40 because this can of Tab has been in my refrigerator sitting at 40 degrees. After 30 minutes, the temperature has risen to 45. How long is it going to take before it's at 60? So now I'm back in my room where it's 72 degrees. My new surrounding temperature is 72 degrees. I guess back to the original situation. And I've got the same differential equation solution. Temperature is something times e to the something t plus something. My temperature, the surroundings now are back to a comfortable 72 degrees. My initial conditions, t sub 0 equals 40. Again, for the third time, I can just plug that in and say 40 equals something times 1 plus 72. Interestingly, I get my constant is, let's see, I found that to be a negative 32. It's a negative number, so interesting. Probably because my can is warming up. It's doing the opposite of cooling. And I mentioned in class, if I change around the order of my uppercase t's in my very first differential equation, if I make this t sub s minus t, it would change the sign on our constant a. So because I chose to do t minus t sub s instead of t sub s minus t, I'm getting this negative value for my constant. But anyway, either way it would be okay. And then finally, my temperature after 30 minutes is 45 degrees, and so everything's plugged in except for that. And here finally I'll actually walk through the algebra steps. I've got this constant, nope, I take it back. I did cheat. And I used this, I plugged it into the equation. I said that when the temperature is 45 degrees, this will be equal to negative 32 times e to the something times 30. I don't know what the value of k is, plus my surrounding temperatures of 72. Here I am going to cheat and just talk you through the algebra. For the third time, subtract 72, divide by negative 32, natural log, and then divide by 30. And when I did this, I got k equals negative 0.00. So far, I'm at Blutarski's GPA 00566, approximately, which gives me the equation that will allow me to answer the question, how long will it take before the can of Tab is at 60 degrees? Plug in my constants. A is negative 32, K is negative 0.00566, temperature of the surroundings 72, and I want to find out when this is equal to 60. So set it equal to 60, and here you can actually see my steps. Subtract 72, divide by negative 32, natural log of both sides, and then finally divide by negative 0.00566, giving us a time of 173 minutes, which translates to almost 3 hours. So it looks like I can take my time and sip my delicious beverage. This lesson has been brought to you by Tab. There's no big secret to taking the calories out of a soft drink. People have been doing that for years. But it took the Coca Cola Company to find a way to put robust flavor in. And it took until now, until Tab. I love this ad from the 70s. This fine gentleman with his bow tie and smoking jacket, with this fancy looking cheese and grapes and crackers as he drinks his Tab Cola from a lovely glass goblet. Well, anyway, if you stuck with me this far, here's a quick sneak preview of what we're going to be doing next week. Suppose, I'm not going to do this, but suppose that there are some microbes on that pizza already, and they're going to double in number in every 24-hour period. Now, the size of the pizza limits. I can't have an infinite number of bacteria on my pizza. And so at some point, there's some population capacity to that pizza. And so even though the bacteria may double and then double and then double, after a while it's going to slow down and approach some upper limit. This is getting at the idea for next week called logistic growth. When we have a cap on our population, we'll have to handle things a little bit differently. But I'll leave that for next week. Thanks for watching. Hope you enjoyed it. Hope it helps with stuff that we're doing and just dealing with equations. But if nothing else, I hope you all have a great weekend, and I will see you on Monday. Bye.